Alright, let's get right into it. Number 12. Within hours of reaching orbit, an astronaut's face begins to visibly swell while their legs grow thinner, a transformation so consistent that flight surgeons gave it an actual nickname decades ago: Puffy face, bird leg syndrome. On Earth, gravity constantly pulls roughly 2 liters of blood and fluid downward into your legs. In zero gravity, that pull disappears entirely, and the body's fluid redistributes upward toward the head and chest within the first 24 to 48 hours of spaceflight, a phenomenon documented extensively by NASA physicians since the earliest Skylab missions in the 1970s. The shift causes visible facial puffiness, nasal congestion resembling a permanent head cold, and a measurable decrease in leg circumference, sometimes called chicken legs by astronauts themselves in post-flight interviews. NASA physician Dr. John Charles, who led human research at NASA's Johnson Space Center for decades, has described the sensation as similar to constantly hanging upside down. The body eventually adapts by shedding what it perceives as excess fluid, but astronauts spend their entire mission with a subtly, permanently altered face, a physical signature of gravity's absence written directly onto their own bodies within the first 2 days of leaving Earth. Number 11. Astronauts consistently report that food loses most of its flavor in orbit, a side effect so pronounced that NASA has had to specifically engineer meals loaded with extra spice just to make them edible. The same fluid shift causing facial swelling also produces chronic nasal congestion throughout an astronaut's entire mission, and because taste relies heavily on the sense of smell working properly, this congestion dulls the perception of flavor dramatically, an effect confirmed through astronaut debriefings compiled by NASA's Space Food Systems Laboratory at Johnson Space Center. Astronauts, including Scott Kelly, who spent 340 consecutive days aboard the ISS during NASA's landmark one-year mission beginning in 2015, have publicly stated in interviews that hot sauce became one of the most requested and valuable items aboard the station, used liberally simply to make food taste like anything at all. NASA's food scientists have responded by developing intentionally over-seasoned space food formulations, specifically compensating for this predictable, universal loss of taste. It means every astronaut who has ever orbited Earth has spent months eating food that, to their own altered senses, tasted like a muted, flattened version of what it actually was. Number 10. Roughly half of all astronauts who reach orbit experience a violent, disorienting nausea within their first day in space, a condition first documented by a Soviet cosmonaut who became severely ill during humanity's very first extended trip beyond Earth's atmosphere. Cosmonaut German Titov, aboard Vostok 2 in August 1961, became the first human to report severe nausea and disorientation caused by weightlessness, describing dizziness and vomiting that nearly compromised his mission, an event that led Soviet space medicine researchers to begin formally studying what is now called space adaptation syndrome. NASA's own research, compiled across decades of space shuttle and ISS missions, confirms the condition affects approximately 60 to 80% of astronauts during their first 2 to 3 days in orbit, caused by the inner ear's vestibular system, which relies on gravity to determine up from down, suddenly receiving contradictory signals it has never encountered before. Symptoms typically resolve within 72 hours as the brain adapts, but astronauts have described the initial experience as feeling like a permanent, inescapable carnival ride, occurring at the exact moment they are also expected to perform complex technical procedures inside a spacecraft worth billions of dollars. Number 9. Astronauts sleep dramatically less than they need to in orbit, and NASA's own internal data shows the overwhelming majority of them rely on sleep medication just to get through a normal mission. A 2014 study led by researcher Aaron Flynn Evans at NASA's Ames Research Center, published in The Lancet Neurology, analyzed sleep logs and medication records from 64 astronauts across 80 space shuttle missions and 21 ISS missions, finding that astronauts averaged just under 6 hours of sleep per night in space, well below the 8 hours officially scheduled and recommended. The same study found that astronauts use sleep-promoting medication on more than half of all mission nights recorded, far higher usage rates than typical for the general population on Earth. The disruption is caused by a combination of factors, including the station's 16 sunrises and sunsets occurring every 24 hours as it orbits the planet, disrupting the body's natural circadian rhythm, along with the constant ambient noise of life support systems that never stop running. It means that for months at a time, astronauts operating expensive, dangerous equipment in a lethal environment are doing so while chronically sleep-deprived, medicated, and biologically confused about when night is supposed to begin. Number 8. Astronauts return from long missions measurably taller than when they left, and the very process that stretches their spine leaves many of them in severe pain and at significantly higher risk of a herniated disc for months afterward. Without gravity compressing the spine, the vertebrae and cushioning discs between them expand and separate slightly, causing astronauts to grow between 3 and 5 centimeters, roughly 1 to 2 inches, over the course of a mission, an effect first formally measured during NASA's Skylab program in the 1970s and confirmed repeatedly since. Researcher Dr. Scott Smith, who has studied musculoskeletal health for NASA's Human Research Program for decades, has noted this rapid elongation places unusual strain on spinal discs that are not designed to expand that quickly. A study published in Spine in 2016 by researcher Douglas Chang and colleagues found that astronauts face a 4-fold increased risk of herniated spinal discs, specifically in the year following spaceflight, compared to the general population. The height gain reverses within weeks of returning to Earth, but for many astronauts, the compression back to their normal size arrives alongside genuine, documented back pain and elevated risk of spinal injury. Number 7. Muscles begin measurably wasting away within days of reaching zero gravity, and even astronauts who exercise for 2 hours every single day still cannot fully prevent the loss. Muscles that support posture and movement against gravity, particularly in the legs and back, have nothing to work against in orbit, and NASA research compiled through decades of Skylab, Shuttle, and ISS missions confirms astronauts can lose up to 20% of muscle mass in certain muscle groups during missions lasting just 5 to 11 days, if no countermeasures are taken at all. To combat this, NASA equips the ISS with specialized exercise equipment, including the Advanced Resistive Exercise Device, developed specifically because standard weightlifting is impossible without gravity, and astronauts are required to exercise roughly 2 hours daily as a mandatory part of their schedule. Despite this rigorous regimen, research published by NASA exercise physiologist Lori Ploutz-Snyder confirms astronauts still experience measurable muscle strength deficits upon return, requiring extensive rehabilitation. It means that maintaining a functioning human body in space is not simply a matter of staying fit. It is a constant, losing battle against a process the body cannot be fully trained to resist. Number 6. Astronauts lose bone density at a rate comparable to elderly osteoporosis patients, except the loss happens roughly 10 times faster, and some of that lost bone may never fully return, even years after coming home. NASA researcher Adrian LeBlanc, working with the university's Space Research Association, published extensive findings throughout the 2000s showing that astronauts lose approximately 1 to 1.5% of bone mineral density per month in weight-bearing bones like the hip and spine, compared to elderly individuals on Earth who lose roughly 1 to 1.5% per year. This occurs because bones, like muscles, require the mechanical stress of gravity to trigger the cellular processes that maintain their density, and without it, the body simply stops rebuilding bone as fast as it breaks it down. A study published by LeBlanc's team in the Journal of Bone and Mineral Research found that some astronauts had not fully recovered their pre-flight bone density even a full year after returning to Earth. For missions to Mars, which would last 2 to 3 years round trip, NASA has publicly stated that current bone loss rates raise serious concerns about astronauts returning with skeletons significantly weaker and more fracture-prone than when they left. Number 5. An astronaut's heart physically changes shape in orbit, becoming measurably more round and spherical, a transformation researchers only confirmed by comparing detailed ultrasound scans taken before, during, and after spaceflight. Cardiologist Dr. James Thomas at the Cleveland Clinic, working with NASA on a study called Vascular Echo, published findings in 2014 in the Journal of the American College of Cardiology showing that the human heart, freed from having to pump blood against gravity's constant downward pull, becomes approximately 9.4% more spherical during long-duration spaceflight, a structural change confirmed through ultrasound imaging conducted aboard the ISS itself. Thomas has publicly described this reshaping as concerning specifically because a more spherical heart is generally a warning sign of heart failure when observed in patients on Earth, though in astronauts the change appears to reverse after returning to normal gravity. The research remains ongoing specifically because nobody yet fully understands what happens to a heart that undergoes this reshaping repeatedly over a multi-year Mars mission, or whether repeated reshaping and reversal could eventually cause damage that does not fully reverse itself. Number 4. Dormant viruses that have been sitting harmlessly inside an astronaut's body for decades, sometimes since childhood, wake up and become active again during spaceflight, and NASA has directly linked this reactivation to the stress zero gravity places on the immune system. Researcher Dr. Satish Mehta at NASA's Johnson Space Center led a study published in 2019 in the journal Frontiers in Microbiology, analyzing saliva, blood, and urine samples from astronauts before, during, and after spaceflight, finding that herpes viruses, including the varicella-zoster virus responsible for chickenpox and shingles, and Epstein-Barr virus, frequently reactivated during missions at rates far higher than seen in the same individuals while on Earth. Mehta's research found this reactivation was directly correlated with elevated stress hormones and demonstrably weakened immune cell function measured in astronaut blood samples during flight. While most reactivations produced no visible symptoms, a small number of astronauts have developed skin rashes directly linked to viral reactivation during missions. NASA has stated this finding raises specific concern for future long-duration Mars missions, where a weakened immune system reactivating a dormant infection would need to be treated using only the medical resources physically present aboard the spacecraft, with no possibility of returning to Earth for treatment. Number 3. Doctors monitoring an astronaut's blood flow in 2019 discovered something nobody had ever confirmed before. Blood in the neck can begin flowing backward or stop moving entirely in zero gravity, and in one case, it formed an actual clot inside a living astronaut's body while still in orbit. Researcher Dr. Karina Marshall-Goebel, working with NASA's Fluid Shift study, published findings in the New England Journal of Medicine in 2019 documenting the first confirmed case of venous thrombosis, a blood clot, discovered in an astronaut's internal jugular vein during a long-duration ISS mission, identified through ultrasound scans conducted specifically to study blood flow in microgravity. The study found that in several astronauts, blood flow in the internal jugular vein slowed dramatically, or reversed direction entirely due to the absence of gravity's normal downward pull, conditions that would typically only be seen in patients with serious circulatory disease on Earth. The clot was successfully treated with blood-thinning medication carried aboard the station, but NASA has publicly acknowledged that a clot breaking loose and traveling to the lungs in orbit, far from any hospital, represents one of the most serious and previously unrecognized medical risks ever confirmed in an active astronaut, discovered only because researchers happened to be scanning for something else entirely. Number 2. NASA conducted an unprecedented experiment comparing genetically identical twin astronauts, one who spent a year in space and one who stayed on Earth, and found that spaceflight actually altered gene expression and the length of protective structures at the tips of human DNA. Beginning in 2015, NASA's twin study compared astronaut Scott Kelly, who spent 340 days aboard the ISS, with his identical twin brother, retired astronaut Mark Kelly, who remained on Earth, involving 10 research teams led by principal investigators including Dr. Susan Bailey at Colorado State University, and Dr. Christopher Mason at Weill Cornell Medicine, with comprehensive results published in the journal Science in 2019. The study found that Scott Kelly's telomeres, the protective caps at the ends of chromosomes that typically shorten with age and stress, unexpectedly lengthened during spaceflight, before rapidly shortening again upon his return to Earth, alongside measurable changes in the expression of thousands of genes related to immune function, bone formation, and DNA repair. Most of these changes reversed within 6 months of returning, but researchers confirmed a small percentage of gene expression changes remained altered even years later. It was the first direct evidence that spaceflight can measurably reach into human DNA itself and change how the body's own genetic instructions are being read. Number 1. Astronauts return from long missions with permanently altered eyesight, a condition doctors have been documenting for over a decade, and NASA has publicly stated they still do not fully understand the cause or have any confirmed way to stop it before a mission to Mars. NASA ophthalmologist Dr. Thomas Mader first formally documented spaceflight-associated neuroocular syndrome, or SANS, in a 2011 paper published in the journal Ophthalmology, describing flattening of the eyeball, swelling of the optic nerve, and folds developing in the retina among astronauts returning from extended ISS missions, findings confirmed through detailed eye scans conducted before and after flight. The leading theory, researched extensively throughout the 2010s by NASA's Human Research Program, is that the same upward fluid shift responsible for facial puffiness and nasal congestion also increases pressure inside the skull continuously for months, physically reshaping the eye and optic nerve from the inside. NASA data indicates a substantial percentage of astronauts on missions longer than 6 months develop measurable symptoms, and in some documented cases, vision changes have not fully reversed even years after returning to Earth. as NASA and other agencies plan crewed missions to Mars, lasting far longer than any current ISS rotation. Officials have openly stated that SANS remains one of the single greatest unsolved medical obstacles standing between humanity and deep space, a condition quietly, permanently reshaping the eyes of nearly every astronaut who has ever stayed in orbit long enough to be affected by it. If you want to see more videos like this, click the video on screen now and make sure to subscribe.